Hello everyone. Um, just to recap, today we'll be going through this video of Andrew Karpati. So just to give a recap, right, what we have learned till now, I'm just trying to remember what all aspects we have covered this far. So in the first video, it was all about how backpropagation works and how do we calculate those gradients and change the value of the data so that at the end, right, um, that loss function or means any parameters that we are trying to reduce, right, how we tweak different values of the neural networks to um, make that value go down or go up. And that's where the concept of or that loss functions comes into the aspect. And if you want to reduce that, how we change different values in the neural networks to achieve that and for the neural networks to learn there. So that was the first video. Means that's kind of like the backbone of how neural network works, how it learns, and that's majorly backpropagation. Next video, the spelled out intro to language modeling, building, make more. So here, the simple problem that we are trying to tackle is how to predict what should be the next word in the sequence. And one of the simplest method that was proposed by Andrew was that we count the number of occurrence of bigrams model. So by bigram, what I mean is say 8 and minutes they are coming one after the other. Minutes and ago are coming one after other, like this here, right? So this is just a simple way of representing the counts of how many of these pairs are coming, and then taking a probability of all of them, and next time if we are getting a word right, we see among those, right, which has the highest probability of coming with that word. So if we get an 8, minutes might have the highest probability, so we predict minutes coming into the picture. But it was just not based on probability. We are trying to do the distribution and randomly trying to um, pick one of them which might occur. So that way we are trying to predict the next words. One and in the same video, means we come with that huge that huge square matrix in terms of the words and the next word that is expected out of that. What is the probability with that? That was one simple way of finding the next word. And the same video we see how we can build that probability matrix that we got using neural networks. We achieve that rather than just going by calculating, right? How we can make the neural network learn to reach to that probability matrix. So that was there. And the third video, then we went about how we can represent these words as embeddings. The one reason why we want to do that is if we go by that probability or the counting way of doing it, right? Um, we were just looking into bigrams, means the words that are coming in pairs. It can be trigram or 4 words coming into the picture, right? So, and the more we have the context of the words, those are coming, right? It's always better at predicting what should be the next word. It's always a better if the amount of information we can score. But obviously that matrix that we see, right, will explode as we go on trigram and everything, and the number of words as well in the vocabulary, right? If it is like lakhs and lakhs of words, right, you can just imagine the size of the matrix that's going to come, and that's where we came up with embedding, where we represent a word with fixed fixed size vectors, and again that's again there is nothing fixed in terms of that should be the size of that vector representing a single word, but we learned how we can represent that, and how we can use that again to train our neural network, so that when we feed in say few words that are coming in the context, right, what should be the next word that should be coming out of it, and train the model based on that. And majorly the concept was around that if the center word is like here 12, we take context words, mean that comes in a certain window size. So say if window size is 2, so we'll take 2 words after this, that is minutes and ago, and 2 words before this, that is last and checkpoint. And again, we are not maintaining the sequence of the words the way they are coming in terms of last and checkpoint come before that. Which one comes before and afterwards, we are not storing that. So the concept was, if we pass on last, checkpoint, minutes and ago, right, there should be a higher probability that we get 12 as the word that should be present here in that way. So that was the context in terms of training the model and everything, where um, we try to get those embeddings, and next time onwards we just push in say 4 words and then try to predict what should be the next word, and in that way we go about it. So that was multi-layer perceptron. In the next video, the activation and gradients and batch norm, this talked about few of the issues that we see in the neural networks, specifically regarding initialization of the neural networks and what are the different challenges that we see there. One was, if we initialize it better, right, the initial loss that we see when it goes through the first round of training the neural network, right, we have as low error as possible. That was one thing. The other issue was regarding tan h being a non-linear function, right? Um, if the value that tan h takes is very high, means it is very closer to 1, right, that neuron becomes dead, because when we try to calculate the gradient, right, it is 1 minus tan squared. So if it is very close to 1, right, so 1 minus 1 square you can take, or very close to 1, right, it becomes a 0. So there is no updation in the tan h neuron. As a result, it becomes dead, and there is no learning that is associated with that. And when the neural network is pretty deep, right, there might be chances that neurons are becoming dead and they are not learning, and it's very tough to figure that out. And that's where one way to solve that problem was patch normalization, where we normalize the value that are going into those tan h function, and make sure that we are not taking very high values near to 1, but it's a Gaussian distribution of the values that it takes. In that way, we make sure that, okay, major neurons are not dead and they are learning. So that was till now. Now we'll go through this video, and anyway, don't worry, I think these are pretty deep things, and it's not easy to grasp all the concepts and everything. Even I at times go through a piece twice or thrice, right? I learn something different. So I think one thing I plan to do is, in the first instance, go through it. The next instance, again, we'll try to go through all the videos so that concepts are somewhat much better ingrained and we consume most of it. So let's go through this.
So today we are once again continuing our implementation of Make More. Now so far we've come up to here, multi-layer perceptrons, and our neural net looked like this, and we were implementing this over the last few lectures. Now I'm sure everyone is very excited to go into recurrent neural networks and all of their variants and how they work, and the diagrams look cool and it's very exciting and interesting, and we're going to get a better result. But unfortunately I think we have to remain here for one more lecture. And the reason for that is we've already trained this multi-layer perceptron, right? And we are getting pretty good loss. And I think we have a pretty decent understanding of the architecture and how it works. But the line of code here that I take an issue with is here, loss.backward. That is, we are taking PyTorch autograd and using it to calculate all of our gradients along the way. And I would like to remove the use of loss.backward, and I would like us to write our backward pass manually on the level of tensors. And I think that this is a very useful exercise for the following reasons. I actually have an entire blog post on this topic, but I'd like to call backpropagation a leaky abstraction. And what I mean by that is backpropagation doesn't just make your neural networks just work magically. It's not the case that you can just stack up arbitrary Lego blocks of differentiable functions and just cross your fingers and backpropagate and everything is great. Things don't just work automatically. It is a leaky abstraction in the sense that you can shoot yourself in the foot if you do not understand its internals. It will magically not work or not work optimally, and you will need to understand how it works under the hood if you're hoping to debug it and if you are hoping to address it in your neural net. So this blog post here from a while ago goes into some of those examples. So for example, we've already covered them, some of them already. For example, the flat tails of these functions and how you do not want to saturate them too much because your gradients will die. The case of dead neurons, which I've already covered as well. The case of exploding or vanishing gradients in the case of recurrent neural networks, which we are about to cover. And then also you will often come across some examples in the wild. This is a snippet that I found in a random code base on the internet where they actually have like a very subtle but pretty major bug in their implementation. And the bug points at the fact that the author of this code does not actually understand backpropagation. So what they're trying to do here is they're trying to clip the loss at a certain maximum value. But actually what they're trying to do is they're trying to clip the gradients to have a maximum value instead of trying to clip the loss at a maximum value. And indirectly, they're basically causing some of the outliers to be actually ignored because when you clip a loss of an outlier, you are setting its gradient to 0. And so have a look through this and read through it. But there's basically a bunch of subtle issues that you're going to avoid if you actually know what you're doing. And that's why I don't think it's the case that because PyTorch or other frameworks offer autograd, it is okay for us to ignore how it works. Now, we've actually already covered autograd and we wrote micrograd. But micrograd was an autograd engine only on the level of individual scalars. So the atoms were single individual numbers. And I don't think it's enough, and I'd like us to basically think about backpropagation on the level of tensors as well. And so in a summary, I think it's a good exercise. I think it is very, very valuable. You're going to become better at debugging neural networks and making sure that you understand what you're doing. It is going to make everything fully explicit, so you're not going to be nervous about what is hidden away from you. And basically, in general, we're going to emerge stronger. And so let's get into it. A bit of a fun historical note here is that today writing your backward pass by hand and manually is not recommended and no one does it except for the purposes of exercise. But about 10 years ago in deep learning, this was fairly standard and in fact pervasive. So at the time, everyone used to write their own backward pass by hand manually, including myself, and it's just what you would do. So we used to write backward pass by hand, and now everyone just calls loss.backward. We've lost something. I wanted to give you a few examples of this. So here's a 2006 paper from Jeff Hinton and Ruslan Selektvinov in Science that was influential at the time. And this was training some architectures called restricted Boltzmann machines. And basically it's an autoencoder trained here. And this is from roughly 2010. I had a library for training restricted Boltzmann machines. And this was at the time written in MATLAB. So Python was not used for deep learning pervasively. It was all MATLAB. And MATLAB was this scientific computing package that everyone would use. So we would write MATLAB, which is barely a programming language as well, but it had a very convenient tensor class. And it was this computing environment, and you would run here. It would all run on the CPU, of course, but you would have very nice plots to go with it and a built-in debugger, and it was pretty nice. Now, the code in this package in 2010 that I wrote for fitting restricted submachines, to a large extent is recognizable, but I wanted to show you how you would, well, I'm creating the data in the XY batches. I'm initializing the neural net, so it's got weights and biases, just like we're used to. And then this is the training loop, where we actually do the forward pass. And then here, at this time, they didn't even necessarily use backpropagation to train neural networks. So this, in particular, implements contrastive divergence, which estimates a gradient. And then here we take that gradient and use it for a parameter update along the lines that we're used to. Here. But you can see that basically people were meddling with these gradients directly and inline and themselves. It wasn't that common to use an autograd engine. Here's one more example from a paper of mine from 2014 called Defragment Embeddings. And here what I was doing is I was aligning images and text. And so it's kind of like a clip, if you're familiar with it. But instead of working on the level of entire images and entire sentences, it was working on the level of individual objects and little pieces of sentences. And I was embedding them and then calculating very much like a clip-like loss. And I dug up the code from 2014 of how I implemented this. And it was already in NumPy and Python. And here I'm implementing the cost function, and it was standard to implement not just the cost, but also the backward pass manually. So here I'm calculating the image embeddings, sentence embeddings, the loss function. I calculate the scores. This is the loss function. And then once I have the loss function, I do the backward pass right here. So I backward through the loss function and through the neural net, and I append regularization. So everything was done by hand, manually, and you would just write out the backward pass, and then you would use a gradient checker to make sure that your numerical estimate of the gradient agrees with the one you calculated during backpropagation. So this was very standard for a long time, but today, of course, it is standard to use an autograd engine. But it was definitely useful, and I think people sort of understood how these neural networks work on a very intuitive level, and so I think it's a good exercise again, and this is where we want to be. Okay, so just as a reminder from our previous lecture, this is the Jupyter notebook that we implemented at the time, and we're going to keep everything the same. So we're still going to have a two-layer multi-layer perceptron with a batch normalization layer. So the forward pass will be basically identical to this lecture, but here we're going to get rid of loss.backward, and instead we're going to write the backward pass manually. Now here's the starter code for this lecture. We are becoming a backprop ninja in this notebook, and the first few cells here are identical to what we are used to. So we are doing some imports, loading the dataset, and processing the dataset. None of this changed. Now here I'm introducing a utility function that we're going to use later to compare the gradients. So in particular, we are going to have the gradients that we estimate manually ourselves. And we're going to have so now here I'm introducing a utility function that we're going to use later to compare the gradients. So in particular, we are going to have the gradients that we estimate manually ourselves, and we're going to have gradients that PyTorch calculates. And we're going to be checking for correctness, assuming, of course, that PyTorch is correct. Then here we have the initialization that we are quite used to. So we have our embedding table for the characters, the first layer, second layer, and a batch normalization in between. And here's where we create all the parameters. Now you will note that I changed the initialization a little bit to be small numbers. So normally you would set the biases to be all 0. Here I'm setting them to be small random numbers. And I'm doing this because if your variables are initialized to exactly 0, sometimes what can happen is that can mask an incorrect implementation of a gradient. Because when everything is 0, it sort of like simplifies and gives you a much simpler expression of the gradient than you would otherwise get. And so by making it small numbers, I'm trying to unmask those potential errors in these calculations. You also notice that I'm using those because that can mask an incorrect implementation of a gradient. Because when everything is 0, it sort of like simplifies and gives you a much simpler expression of the gradient than you would otherwise get. And so by making it small numbers, I'm trying to unmask those potential errors in these calculations. You also notice that I'm using B1 in the first layer. I'm using a bias, despite batch normalization right afterwards. So this would typically not be what you do because we talked about the fact that you don't need a bias, but I'm doing this here just for fun because we're going to have a gradient with respect to it, and we can check that we are still calculating it correctly, even though this bias is spurious. So here I'm calculating a single batch, and then here I am doing a forward pass. Now you'll notice that the forward pass is significantly expanded from what we are used to. Here the forward pass was just here. Now the reason that the forward pass is longer is for two reasons. Number one, here we just had an f dot cross-entropy, but here I am bringing back a explicit implementation of the loss function. And number two, I've broken up the implementation into manageable chunks. So we have a lot more intermediate tensors along the way in the forward pass, and that's because we are about to go backwards and calculate the gradients in this backpropagation from the bottom to the top. So we're going to go upwards, and just like we have, for example, the logprops tensor in a forward pass, in a backward pass we're going to have a dlogprops, which is going to store the derivative of the loss with respect to the logprops tensor. And so we're going to be prepending d to every one of these tensors and calculating it along the way of this backpropagation. So as an example, we have a bn raw here. We're going to be calculating a dbn raw. So here I'm telling PyTorch that we want to retain the grad of all these intermediate values, because here in exercise 1, we're going to calculate the backward pass. So we're going to calculate all these d variables and use the CMP function I've introduced above to calculate the gradients in this backpropagation from the bottom to the top. So we're going to go upwards, and just like we have, for example, the logprops tensor in a forward pass, in a backward pass we're going to have a dlogprops, which is going to store the derivative of the loss with respect to the logprops tensor. And so we're going to be prepending d to every one of these tensors and calculating it along the way of this backpropagation. So as an example, we have a bn raw here. We're going to be calculating a dbn raw. So here I'm telling PyTorch that we want to retain the grad of all these intermediate values, because here in exercise 1, we're going to calculate the backward pass. So we're going to calculate all these d variables and use the CMP function I've introduced above to check our correctness with respect to what PyTorch is telling us. This is going to be exercise 1, where we sort of backpropagate through this entire graph. Now, just to give you a very quick preview of what's going to happen in exercise 2 and below, here we have fully broken up the loss and backpropagated through it manually in all the little atomic pieces that make it up. But here we're going to collapse the loss into a single cross-entropy call, and instead we're going to analytically derive, using math and paper and pencil, the gradient of the loss with respect to the logits. And instead of backpropagating through all of its little chunks one at a time, we're just going to analytically derive what that gradient is, and we're going to implement that, which is much more efficient, as we'll see in a bit. Then we're going to do the exact same thing for batch normalization. So instead of breaking up BatchNorm into all the little tiny components, we're going to use pen and paper and mathematics and calculus to derive the gradient through the BatchNorm layer. So we're going to calculate the backward pass through BatchNorm layer in a much more efficient expression instead of backward propagating through all of its little pieces independently. So that's going to be exercise 3. And then in exercise 4, we're going to put it all together. And this is the full code of training this 2-layer MLP. And we're going to basically insert our manual backprop, and we're going to take out loss.backward. And you will basically see that you can get all the same results using fully your own code. And the only thing we're using from PyTorch is the torch.tensor to make the calculations efficient. But otherwise, you will understand fully what it means to forward and backward a neural net and train it. And I think that'll be awesome. So let's get to it. Okay, so I ran all of the cells of this notebook all the way up to here. And I'm going to erase this, and I'm going to start implementing backward pass.
I just ran this to make sure we are initialized and we reach this state.
Starting with dlogprobs. So we want to understand what should go here to calculate the gradient of the loss with respect to all the elements of the logprobs tensor. Now, I'm going to give away the answer here, but I wanted to put a quick note here that I think what would be most pedagogically useful for you is to actually go into the description of this video and find the link to this Jupyter notebook. You can find it both on GitHub, but you can also find Google Colab with it. So you don't have to install anything. You'll just go to a website on Google Colab, and you can try to implement these derivatives or gradients yourself And then if you are not able to, come to my video and see me do it. And so work in tandem and try it first yourself, and then see me give away the answer. And I think that will be most valuable to you, and that's how I recommend you go through this lecture. So we are starting.
I will come back in a minute. So we need to calculate the t log drops. So just to get a hang of what's happening here is, one second,
shouting.
तुझे मेरे बारे में वो सब पता है जो मैंने कभी किसी को नहीं बताया. You know you've been my best buddy since forever.
मैंने चाहा तुझे खता नहीं मेरी खता है कि तुझे पता नहीं
so last no
खता नहीं पता नहीं तेरे नाम प्रीता लाई ओ तेरे नाम प्रीता लाई खबर तेरे नाम प्रीता लाई माही चल खबर नहीं ओ कितने सारे तैया ओ कितने सारे तैया खबर नहीं माही चल खबर नहीं तेरे नाम याद प्रीता लाइया बेमाही तन्नो खबर नहीं मैंने चाहा तुझे खता खता के तुझे पता नहीं मैंने चाहा तुझे खता खता के तुझे पता नहीं कुछ दिन में यार पुराने की हो गया की हो गया की हो गया हो तेरे नहीं क्यों कुछ ठिकाने की हो गया की हो गया की हो गया हो, हम किसे कहती फिक्र नहीं बेमाही तैਨੂੰ खबर नहीं
So I'm getting confused between so we get an array here, I would say a 2D array, and then from each of those 2D array, right, we take the range, so this goes 0, 1, 2, 3, 4, and the column that is the actual response and what is the value that we are getting out of it, right? And then we are calculating the mean. So it's in the microgrid example that we were doing, right, it was at individual number level. Here what we are doing is okay, so for each for each of the value, right, if this value was x, right, okay, for this calculating for each of, I think d log probs that will be calculated, that will be with respect to each of these values. So say log probs is equal to, again a very crude way of taking it, but 0.2, 0.3, 0. I'm just making it up. Okay, this is one. This is one of the things. Okay, sorry. So this is the 2D array. Say initially we got, so this is supposed to be the one. This is the next one. This is the third one. So these are the three examples that we have, and for each example, right, this was supposed to be the answer. This was supposed to be the answer. This was supposed to be the answer. That's what we are doing here. So this is the log props. Now we need to calculate the loss. Loss is taking this one, and this one. These were the three, and doing a mean of it. Okay, so I'm just thinking d log probs, right? Here this d log probs, right? Means I can look at the video and see him calculating, but I want to figure that out. So the d log prob will be based on, say this was supposed to be the response. Mm, so if I increase this value, right, the loss reduces because obviously the negative sign here. If we increase this value and increase it, so based on this, because we are not taking any other, so they don't have any impact on the loss. Loss is directly impacted by either this value, or this value. So if we have to calculate based on this individual, okay, so let's take that. So a is equal to 0.2, b equal to 0.3, c equal to, again, let's take, sorry, let's take different values here. It should not be the same. 0.5, 0.1, 0.04, 0.005. I'm just making it up. 0.2, 0.01, something like this. Okay, so a is 0.2, b is 0.1, and c is 0.001. Now we are doing a plus b plus c by, sorry, by 3 is negative of this. That's what that says, right? So I think the d log probs, right? D log probs should be a array of 3 values, and that should be like d loss by dA, d loss by dB, d loss by dC. I think so. Let's calculate that first and then we'll see. So d loss by dA, right, will be that's anyway simple. So d a plus b plus c by d a, it will, and 1 by 3 we can take out. Okay, like this. So here it will be equal to 1 by 3 and 2 e a by dA will be 1. Okay, I mean this is d a by dA plus dB by dA plus, that's how addition rule in differentiation works, right? So dA This will be equal to 1 by 3 into dA by dA is 1 plus dB by dA is anyway 0 and dC by dA is also 0. Okay, so it is 1 by 3 itself, and this is 1. Okay, so there, right, and the same stands for all of them. So this is d loss by dA, right? In the same way, d loss by dB will be 1 by 3 and d loss by dC will be equal to 1 by 3 and into out dot grad. That's if you remember that, right? So d loss by d loss, that will be anyway equal to 1. So I think we are good here. So below, so it should be all means d loss will be equal to 1, means d loss by d loss or loss dot grad, that we say d loss by d loss, that is that will be anyway 1. So here it will be all 1 by n. But there is a negative sign to it. Don't forget this. So loss, it's minus 1 by 3, okay? It's always minus 1 by 3, so it will be also minus 1 by 3, minus 1 by 3, minus 1 by 3, minus 1 by 3, minus 1 by 3. So, so d log probs will be equal to, it will be just an array in range of n. Where is n? N is the batch size, okay? And I don't think we need this one. It should be 1 divided by n negative sign. This should be the d log probs. So we need to calculate MP compare. This is a string log probs. Hopefully. Okay, that is false. Oh no, sorry, not cred. That is also false. What is the value it's taking? Okay. At least we calculated these values because based on the as I told here, right? Um, DA, right? So this will be because of this the value of loss is changing, but because of these, right, the values are not changing, so those will be zero. So that's what is happening. So you see, right, 0.0312, where it went, so we calculate 0.0312 itself, but it should be placed here. So the output that they are expecting, right, will be output that they are expecting is, because based on A, it should be minus 1 by n, comma 0, comma 0. Okay. We, here it should be minus 1 by n, and this is 0. So this is what they are expecting. Oh, what happened with this individual? Now if you print that, right, see, this is the output that was expected. Okay, so we can take this simple p dot zeros is n comma n. So embedding size. So this 27 vocabulary has just 27 word, is it? So it's 32 by 27, so 32 examples for each batch size is 32, right? For each 32 examples, right? We have 27 words in the vocabulary, and it is trying to make a prediction of which one of those it is. So let's just initialize it for the time being. So we are initializing all of them to 0, and then what we want to do, right? In range of 32. YB is not defined at the same. Oh, sorry, it's capital. So, just to explain, so this is 32 in size. For each of these row, right, 18th column should be 1. So, um, I comma zip. First is that range 32, comma y b. Print I comma j. Tensor dot item. It was, I believe. Yo. It was supposed to be a function. Yes. So what we can do for this, right? D log probs I comma j should be equal to minus 1 divided by n. That's what it is. This is what is the let it be here. Oh, sorry, NPL. See, now we are getting those values, right? Remove this, remove this, remove this, remove this. Now if we do, okay, I deleted that as well. If I do compare log probs d log probs log probs, I think now, so for each of the see, so it was a true, so they all matched. So the intention with this is that for all of these values that we get, right, so here it's log probs. I'll just remove this, remove this, remove this. Where it went. So for each value that we were getting here, right, we are trying to predict how do they impact the loss for each of the values that we get here. We are trying to predict, and the reason for that will be the weights that are associated with all of those. So there will be weights that will be associated to calculate this and this and this and this and everything. So wx plus b giving this, and out of that we are taking that one as a loss of that. Okay, let's see what Karpati has to say.
Starting here with d-log props. Now, d-log props will hold the derivative of the loss with respect to all the elements of log props. What is inside log props? The shape of this is 32 by 27. So it's not going to surprise you that d-log props should also be an array of size 32 by 27 because we want the derivative of the loss with respect to all of its elements. So the sizes of those are always going to be equal. Now, how does log probs influence the loss? Okay, loss is negative log probs indexed with range of n and yb, and then the mean of that. Now, just as a reminder, yb is just basically an array of all the correct indices. So what we're doing here is we're taking the log props array of size 32 by 27, right? And then we are going in every single row, and in each row we are plucking out the index 8 and then 14 and 15 and so on. So we're going down the rows, that's the iterator range of n, and then we are always plucking out the index of the column specified by this tensor yb. So in the 0th row, we are taking the 8th column. In the first row, we're taking the 14th column, etc. And so log probs at this plucks out all those log probabilities of the correct next character in a sequence. So that's what that does, and the shape of this, or the size of it, is of course 32, because our batch size is 32. So these elements get plucked out, and then their mean and the negative of that becomes loss. So I always like to work with simpler examples to understand the numerical form of the derivative. What's going on here is once we've plucked out these examples, we're taking the mean and then the negative. So the loss basically, if I can write it this way, is the negative of, say, a plus b plus c, and the mean of those three numbers would be, say, would divide 3. That would be how we achieve the mean of 3 numbers a, b, c, although we actually have 32 numbers here. And so what is basically the loss by, say, like dA, right? Well, if we simplify this expression mathematically, this is negative 1 over 3 of a, and plus negative 1 over 3 of b. Plus, you can see that if we don't just have a, b, and c, but we have 32 numbers, then d loss by d, every one of those numbers is going to be 1 over n more generally, because n is the size of the batch, 32 in this case. So d loss by d log probs is negative 1 over n in all these places. Now, what about the other elements inside log probs? Because log probs is a large array. You see that log probs, that shape is 32 by 27, but only 32 of them participate in the loss calculation. So what's the derivative of all the other, most of the elements that do not get plucked out here? Well, their loss intuitively is 0. Their gradient intuitively is 0. And that's because they did not participate in the loss. So most of these numbers inside this tensor does not feed into the loss. And so if we were to change these numbers, then the loss doesn't change, which is the equivalent of way of saying that the derivative of the loss with respect to them is 0. They don't impact it. So here's a way to implement this derivative then. We start out with torch.zeros of shape 32 by 27, or let's just say, instead of doing this, because we don't want to hard-code numbers, let's do torch.zeros like log probs. So basically this is going to create an array of zeros exactly in the shape of log probs. And then we need to set the derivative of negative 1 over n inside exactly these locations. So here's what we can do. The log probs indexed in the identical way will be just set to negative 1 over 0 divide n, right? Just like we derived here. So now let me erase all of these reasoning. And then this is the candidate derivative.
This is one way above, and that was nice. So we can take this itself. Let's see. So the zeros underscore like, so that we don't need to plug in values. And here we take log prop, so it will create that 2DRF all the zeros, and how we were initializing it here, right? We can do directly. So instead of the log probs range of ny be equal to and we'll get the same thing here as well. It's the same but much more cleaner way of getting it.
For the log probs, let's uncomment the first line and check that this is correct. Okay, so CMP ran, and let's go back to CMP, and you see that what it's doing is it's calculating if the calculated value by us, which is dt, is exactly equal to t.grad as calculated by PyTorch. And then this is making sure that all of the elements are exactly equal, and then converting this to a single Boolean value, because we don't want a Boolean tensor, we just want a Boolean exact, is exactly equal to t.grad as calculated by PyTorch. And then this is making sure that all of the elements are exactly equal, and then converting this to a single Boolean value, because we don't want a Boolean tensor, we just want a Boolean value. And then here, we are making sure that, okay, if they're not exactly equal, maybe they are approximately equal because of some floating point issues, but they're very, very close. So here we are using torch.allClose, which has a little bit of a wiggle available, because sometimes you can get very, very close, but if you use a slightly different calculation because of floating point arithmetic, you can get a slightly different result. So this is checking if you get an approximately close result. And then here we are checking the maximum, basically the value that has the highest difference, and what is the difference in the absolute value difference between those two. And so we are printing whether we have an exact equality, an approximate equality, and what is the largest difference. And so here, we see that we actually have exact equality. And so therefore, of course, we also have an approximate equality, and the maximum difference is exactly 0. So basically, our dlogprobs is exactly equal to what PyTorch calculated to be logprobs.grad in its backpropagation. So far, we're doing pretty well. Okay, so let's now continue our backpropagation. We have that log